Hello, I'm N J Wildberger and we're here at the University of New South Wales. This is Chapter 4 of our linear algebra course, MATH1131, and we're having a look at this particular problem that is in the chapter on linear equations and matrices. So it's problem number 2. It's determine algebraically whether the following systems of equations have a unique solution, no solution, or an infinite number of solutions, and draw graphs to illustrate your answers. And we have 3 different examples of systems of linear equations. These are pretty small systems because each one only has 2 equations in 2 unknowns. And so each one of those equations represents a line in the plane that we can draw very explicitly. So we can solve these systems algebraically using the row reduction technique, sometimes called Gaussian elimination. And then we can see how the algebraic side of things actually corresponds to the geometry and how the pairs of lines relate to each other and give solutions or no solutions or an infinite number of solutions. All right, so let's start with the first case where we have the equations 3x1 plus 2x2 equals 6 and 9x1 plus 6x2 equals 36. Now I want to show you first of all how we would do this using just high school algebra, so that you can see that the row reduction system that we are doing sort of more officially is in fact really just very similar to what you would have done in high school. So in high school you would have said, all right, let's call these equations, say 1 and 2, and you would have probably taken one of the equations and subtracted multiple of the other. So if we take equation 2 and we subtract 3 times equation 1, what would we get? We would get 9x1 minus 3x times 3 is 9, so it would be 0x1. And 6x2 minus 3 of these would be plus 0x2. And 36 minus 3 of those is 18. We would have gotten the equation 0x1 plus 0x2 equals 18. And there are no solutions to this. Right? There are no solutions. And let's have a look at the picture. So the diagram, we're going to use axes x1 and x2 rather than x and y because that's what's involved actually in the problems. All right, what does the first equation represent? It's a line. And it's easiest probably to graph such a line by looking at the x and y intercepts. So if we set x2 equal to 0, we get x1 equals 2. It's telling us that this line goes through the point 2, 0. And if we set x1 equal to 0, then we can solve for x2. We get x2 equals 3. So there's 1, 2, 3. All right, so it goes through that point there. And then the line looks something like this. All right, that's the first line. And what about the second one? Well, 9x1 plus 6x2 equals 36. Again, we could look for x and y intercepts. So if we set x2 equal to 0 and solve for x1, we get x1 is 36 over 9, which is 4. That would be over here. And if we set x1 equal to 0, solve for x2, we would get x2 equals 6, which would be up here somewhere. Okay, and so if we join those 2 points, then we get the second equation. And we can see that now it's no surprise that there are no solutions because these are parallel lines. So we have parallel lines. So no solution. So good, that's what we would have done in high school. Now let's see how we would approach this problem using the matrix framework that we prefer here in this linear algebra course. So we're going to rewrite this system in matrix form. In matrix form, we could write this equation as 3, 2, 9, 6 times x1, x2 equals 6, 36. let's have a look at that. All right, so over here we have a matrix times a vector equals another vector. You can see that the matrix is just the matrix of coefficients. This vector here is the vector of the variables, which are x and y. And this vector over here is the right-hand side. And let's make sure that we understand that this is really the same as that, because if we multiply out this matrix, we get 3 times x1 plus 2 times x2 equals 6. That's the first row. And the second row, 9x1 plus 6x2 equals 36. All right, good. So from this, we would then say the augmented matrix is, well, we put these two things together, 3, 2, 9, 6. That's the matrix of coefficients on the left-hand side, and then a line, and then the right-hand column, 636. So this augmented matrix contains the same amount of information as the matrix form, which contains essentially the same information as the original pair of matrices. All right, so now we row reduce. How would we row reduce? Well, we're going to perform some operations. And what we're going to do is essentially the same thing that we did over there. We're going to replace row 2 with row 2 minus 3 times row 1. Right. So this is just a way of describing what we're going to do to this matrix to get the new matrix over here. All right. So the first row is going to stay where it is. And the second row, this minus 3 times the first row. So 9 minus 3 times 3 is 0. And 6 minus 3 times 2 is 0. And 36 minus 3 times 6 is 18. And you can see that's pretty well exactly the same kind of thing that we got up there. But here we're doing it in the context of this row reduction or Gaussian elimination at the level of augmented matrices. And now at this stage here, we can see that we have a row, this one here. This row has zeros on the left of the bar and 18, something non-zero, on the right. And that means that it corresponds to an equation of the form 0x1 plus 0x2 equals something non-zero, namely 18. And from this row, we can see that there cannot possibly be a solution. So we can say no solution from the existence of such a row like this. And again, the reason is because we have these two parallel lines.